I wanted to walk through some more examples. You should understand the method of joints now, so the point of these examples is to now start thinking through what designs are going to be best for your spaghetti bridge. So how the different angles and truss structures are going to support loads and why one design would be better than another design. So we're going to be comparing a few different designs that all have similar dimensions and the same load, the same span, and just see how these different bridges compare. Think about where they're going to fail, and if you're going to build a bridge, where you would want to add extra supports, where you have wasted material that's not being used so that you can create the most efficient design. Starting out, we're going to look at the Gambrel roof truss shown. So the Gambrel, kind of a barn sort of a truss, and you've probably seen these before. And what we have is a symmetric loading where we have some loads on every single joint in here. Starting out, we're going to solve for the reaction at the supports. So what reaction is going on at A and H? There are no forces in the x direction, so we can eliminate HX. This is symmetrical, and so we can just put half of that load on each side. So we have 1,200 pounds going up on each side. Now that we have the external loads, we'll start from the edge and work our way to the inside, solving for the forces acting on each joint that will show us where compression is, where tension is, where zero force members are. Starting from the side, what goes up must come down. Now 1,200 is going up, but only 300 is going down. That means we need a little bit more weight coming down to balance out that 1,200 force. So you see that compressive shell start to develop around the edge of it. And of course, if we're pushing to the left, that means AC is going to be in tension. So tension is developing along the base of this structure, and we have a compressive ring that's starting to form around the edge of it. This is a 3, 4, 5 triangle. You can see 6 feet high, 8 feet wide, so 6, 8, 3, 4. And we can simply use the ratio of that 3, 4, 5 triangle to solve for what we need. So 300 plus 900, 3 plus 9 is 12. That's just balancing the forces in the y direction. And once we know that AB going down has to be 9 coming down, we can walk around the rest of that triangle and see that the other sides are going to be 1,500 pounds and 1,200 pounds. Again, AB is in compression, AC is in tension, and you'll see this over and over again where you have tension along the base and compressive forces around the rim of your bridge. Once we have A solved for, what is the next joint we can look at? If we come up to B, there are 2 unknowns, 3 unknowns at B, so we can't solve for that yet. So let's come down here and look at C. Looking at C, we have tension that needs to be pulling in each direction. There's nothing underneath C. That means that CB is a zero force member. Okay, so there we have tension and tension. It's going to be the same across the whole base. There's our zero force member, and the next node that we should go to is B, because we only have 2 unknowns at B. So here's B. We have 1,500 coming up. Now look what happens to this 1,500 as we're dipping down. So BD is at a shallower angle. So what's going to happen to that 1,500? Well, some of that 1,500 is getting pushed into the structure itself. So that 1,500 is now getting pushed down into BE. BE gives 60 pounds of compression, and BD is only 1,200. So isn't that interesting? We've gone from 1,500 to only 1,200 by pushing some of that force down internally into the structure. If you watch some of the YouTubes of what wins the spaghetti bridge competitions, you'll see a lot of bridges that have kind of bicycle spokes. And that's what those bicycle spokes are doing. They're pulling some of that external force down into the structure itself. So every time we take that member and make it a little less vertical means it's going to be a little bit smaller because we're trying to support these vertical loads here. Okay, walking through it a little bit more. So we went from A to C up to B, and what's the next one that we should do? So if we come down to E, there's 1, 2, 3 unknowns. We can't do E yet. Up here at D, we have only 2 unknowns yet left. Remember also that this guy is symmetrical, so that symmetry should help you out here. Because it's symmetrical, we're going to have 1200 on each side, and you can then add up the x and y components and see that the center in this case ends up coming out in tension. So that's kind of an interesting thing. So we have DF is in compression, and it's 1200 pounds, just like the other side. So we have that compression, compression, compression going around the whole edge in compression. And how these guys are pushing up, we end up having tension in the center. So DE in the center is in tension. And that has to do with how these external loads are applied. And really, you shouldn't think of just one system and one scenario of external loads. As you change how this bridge is loaded, all of the internal forces are going to be changing too. So it's good to work through a couple different loading scenarios and see how those are changing the internal forces here. Recognizing the symmetry, we can fill in the rest of our structure. Looking at this, where is it going to break? It's going to break somewhere along the edge here, 1200, 1200, 1500, 1500. This guy right here, AB or FH, that's where the majority of the force is being held. And why would that be? So it has to do with being over here at the edge and the type of external load that's happening. Plus, this is up in kind of the vertical direction. So anything that's in the same direction as your forces, that's what's going to be holding up most of that vertical weight. So if you want to reinforce this bridge, or if you want to see what's going to break first, you'd want to reinforce, maybe make this piece of pasta a little bit thicker than the others. Okay, if you look at some of the problems in the book, you'll see similarities. So we have 3, 6, 6, 6, 3. Here's another bridge that has pretty much the same external loading. We have 8, 8, 8, 8. So the same span in both cases, the same external loading in some cases. And the only difference here between the Gambrel and the Howe roof is we have not changed the angle. We have just a straight, flat roof line here. Comparing these two, what is going to support the largest pile of snow on top of it, do you think? Would it be better to make your roof taller? Or would it be better to make your roof more round? This would actually, the Gambrel roof would have less material. It would be cheaper to make. If you add up the lengths of all of these boards and see how much wood you'd have to buy for this, it would be cheaper to make. But if you look at the forces it supports, which one is more likely to collapse under a large load? So those are some of the questions that you should be asking yourself as you finish your analysis of these different structures. Here's a comparison of two very similar designs, 3 to 1.5, and we have a load applied in the middle, 1,000 newtons in the middle, 500 to 500. If you crank through this one, these are the forces, so compression along the edge, tension along the base, and we end up with a lot of zero force members on the sides. You can put this into Inventor software and actually load it and see where it's going to break. Now in statics, we're assuming that each of our members is not deforming. When you get to mechanics and materials, you will do analysis where you see what happens when the members actually start bending. So this is a little bit more than what we're doing in statics, but it's still interesting to see that those zero force members are showing up as blue. That means they're not holding up anything. And where you see the stress developing is around the edge. Remember those compressive pieces, that's where it's probably going to break first. And then here in the center, that is underneath a lot of tension. So you can kind of see highlighted how this is going to start bending and eventually break. Here we go. What if we had the same structure, only we made it a little bit taller, so 6 instead of 3? What would that do to our internal load? Let's go ahead and compare those two, a tall one and a short one. So same thing. When we put this taller, we've actually decreased the amount of compression along the edge. And our largest tension right here, this red area, the 1000, is now where it's going to break. So it's a very different force distribution as we're making this taller. Here's a direct comparison, short versus tall. The short, we're at over 1,000 newtons in compression, 1,118. This decreases to only 700, 707.1, that's a 0.1. So as you make it taller, the compressive load becomes smaller. This is why you want to make a tall bridge or a tall roof. It actually decreases how much load is in here. We still have 1,000 in the center. We still have zero force members. Tall, look at this. We have only 500 newtons tension instead of 1,000. So isn't that interesting? This is the same load, 1,000 newtons down, 500 newtons on the side, but making it taller, remember we're supporting a load in the y direction, a vertical load. So as you make it taller and taller, you significantly decrease the amount of tension that's in here. You're not playing tug-of-war as much. And you significantly decrease the amount of stress in our compressive members around the edge. But of course, as you make it taller, it's more expensive. It takes more material to build these things as it gets taller. Here's a comparison of those finite element analysis of these two bridges. So you can see how that force is being transmitted, how it's being deformed. Here is the Fink roof truss. And again, we'll do a couple different scenarios with different heights. So here we've taken the load and we're dividing it among these two nodes. So 500 and 500 down, 500 and 500 up. So we're still supporting 1,000 Newton load. We're just kind of dividing it between these two pin supports. So here we can do the length of wood that would be required and think about how expensive it is to build versus how much the forces are in here. So once again, we have a short roof and a tall roof. 700 versus 900. Short is worse. Short is going to break first. Look at the internal forces, 527 versus 559. So this is a little bit larger, but it's not too big of a difference. The bigger difference you see in the very outer edge. And then along the bottom, what we have, 750 versus only 500. So that's a pretty significant difference. Just making it a little bit taller has significantly decreased the tension that is here. We have 333 instead of 500. So overall, we're seeing again a taller structure is going to be under a smaller load. Here's another comparison of these guys. So what about this center design versus without the center design? 500, 500, 500, 300, 0 and 1,000. We're taking that 1,000 and we're splitting it, 500 and 500, 700, 700. So the outside edge of this looks pretty similar, but changing this internal structure, you can take that big force and you can kind of split it apart if you want to. Okay, so hopefully this is giving you kind of an idea for some of the pros and cons of the different structures that are out there and how they compare to one another. There's an infinite number of different truss structures that you can choose between, so have fun designing your bridge, and we'll see you next time.